Okay, so real numbers, you guys have been talking about real numbers your entire life. You just know them as different things. So we have what we start off with as this entire set. This is a huge category of real numbers where you've got a breakdown of multiple parts and one part or one situation. So for here, we start off with the smallest value, which is the natural values, or smallest category, not smallest value. Smallest category is what we call our natural numbers. And natural numbers are whole values starting at 1. So when you start with the number 1, so you go 1, 2, 3, 4, and it just keeps going on and on and on. That's your set of natural numbers. Okay, then we progress up to the next set, the whole number. The only difference between the natural number and the whole number is what value? Anybody know? 0. Whole numbers are 1, 2, 3, 4, but they also include 0. So you have 0, 1, 2, 3, 4, 5, and it just keeps going. Okay? Those are your whole numbers. Then we introduce our integers. Integers are also 0, 1, 2, 3, 4, 5, so on and so forth, but what else do they include? Anybody think they know? Negative numbers, very good. So you have like -5, -4, -3, -2, -1, 0, 1, 2, 3, and it just keeps going on and on and on. So you've got your 0, you've got your positive values, but you also have your negative values. That's what integers are called. So if I say, hey, what do we call the number 3? You can call it a natural number, you can call it a whole number, you can call it an integer, you can also call it a rational number, because a rational number is going to include all of this information plus the addition of fractions and decimals. So if we have 1/2, 1/2 is considered to be a rational number. 0.3 repeated, that is a rational number. Okay, 2 1/4 is a rational number. -7.8 is a rational number. But then in between there you also still have your integer values like -7, -15. You've got your whole numbers. You've got 11. You've got, I don't know, 29. You've got 0. Okay, you've got 4. You've got all of these kinds of values that are considered to be rational. So if it is a natural number, it is also known as a whole, an integer, and a rational. Okay, now rational numbers, what's really important to remember with rational numbers, they are, when converted to a decimal, they either repeat or terminate. That's really important to make sure you keep in mind that with rational numbers, and I'm going to put this here, rational numbers repeat or terminate. Rational numbers either repeat or terminate when they are in their decimal form. Okay, they can go on forever and ever and ever, but they have to either repeat in decimal form or terminate as a decimal value. Okay, that's our rational numbers. Now, off to the side over here, we have a set called irrational. Irrational numbers, they are just values that are going to have no repetition. No repetition, no end. They never stop and they never repeat. They go on forever and ever and ever. Our most famous irrational number is pi. Pi is a value that, yes, we know it as 3.14 because we estimate it, but it actually is a number that goes on forever and ever and ever. Okay, if we have the square root of 3, or we'll say 31. Square root of 31. Square root of 31 is an irrational number because when we take the square root, it never stops. It keeps going on forever and ever and ever. Okay. Fractions can also be irrational. So pi in fraction form is just 22 over 7. That is an irrational number. So even though it is a fraction, when it's converted to a decimal, it does not repeat and it does not stop. It just keeps going on. So any value that has no ending point and no repetition, no rhyme or reason, no rationality about it, it's an irrational number. And all of these numbers are a part of what we call real numbers. What we're going to be focusing on for this unit is the concept of roots. Okay, but before we move on to that, what I want you guys to do is taking a look here at these problems 1 through 4, I want you to identify all sets that those real numbers belong to. Okay, so identify every single category that it represents. Go ahead and do that now on your own. All right, let's go over this. So for problem number 1, it's 0.252525, and it's just going to keep going on in that pattern. So what category does that represent? Michael, what category would that be? Rational. And that's the only category that can go into. Because it is a decimal, it cannot be considered to be an integer or a whole number or a natural number because those don't have any decimal values in there. So the next setup would be for the rational numbers because it does repeat. So that is going to be a rational value. Okay, what about 0? What categories do 0 belong to? Armando, what category did you put for 0? Very good. So whole number definitely belongs into the whole number set. And because it belongs into the whole number set, it means it also belongs for the integers and it belongs for rationals. Okay, so we have whole numbers, integer, and rational. What about the square root of 3? The square root of 3. What set is square root of 3 going to belong to? Ray? Square root of 3. It's not going to be rational. It's actually going to be an irrational number. Because if you take a root, 3 is not a perfect square. There is nothing that you can multiply by itself to give you the value of 3. Okay, so it's going to be an irrational number because it's going to give you a decimal value that's going to extend on forever. Okay, so this is irrational. Okay, what about number 4, the negative square root of 16? So, Jung, what do you think? Rational and integer. Very good. So if we were to simplify this, the negative square root of 16, square root of 16 is 4, right? Because 4 times 4 is going to give you 16. So this just becomes a negative 4. Okay, because the negative is on the outside. So negative 4 happens to be an integer, which also happens to be a rational number. Okay, any questions about identifying the groups that it belongs to? All right, let's go on then to the concept and idea of what roots are. So roots are, or radicals, as you're going to hear me call them, radicals. It's just the representation of things like square roots, cube roots, roots of the 4th, 5th root, 6th root. You have them going all the way up to what we call nth root. You can take a root to any value. Now, a root, guys, is just an exponent. A square root is actually an exponent of 1/2. Okay, a cubed root is an exponent of 1/3. A 4th root is an exponent of 1/4. So they're just fractional exponents that you're actually taking. But what it means is that you're identifying a value that if you multiply it by itself will give you what we call the radicand. Okay, so this symbol, this root symbol that you see, it's actually called the radical sign. So whenever you hear me use the words radicals, it's implying that there is a root involved. Okay, the radicand is just the value that is inside of your radical symbol. Okay, so if I have square root of 16, 16 right here is my radicand. It's the value that's inside of the radical. Okay, when I take the radical or the root of 16 and get 4, that would be denoting what the root's value is. Okay, let's move on to the back. Go ahead and flip it on over to the back. So what we're going to be doing here is we're going to break these down based off of perfect squares. We have to identify a value that we can multiply by itself to equal this perfect value here. Okay, and I'm going to be giving you the list of perfect squares and perfect cubes at the end of class today for you to study from. But square root of 100, what times itself is going to give us 100? Divya? 10. Now, when we talk about roots, it's not just 10. So yes, 10 is going to be able to give me 100. 10 times 10 is going to give me 100. But there's something else that can also give me 100. Anybody? What about negative 10? Can I multiply negative 10 times negative 10? Is that going to equal 100? Yeah, because a negative times a negative will equal a positive. So when you're taking a root, a square root, you have to understand that it's not just the positive, but it's also a negative that can be included. So you'll see answers written as the following: a plus sign and a minus sign. That means a positive 10 and a negative 10 are possible solutions to the square root of 100. Now, if I have a negative symbol in front, then that means that the only answer I'm looking for is the negative response. Okay? So square root of 25 is what? 5, but we want the negative only, so that would be negative 5. Now, even though this one happens to be a decimal, if you pretend like the decimal is not there and it was just 121, what times itself would equal 121? Thank you. 11. But we have a decimal. It's 1.21. So what do you think it's going to be instead? Not 11, but 1.1. So we have a plus or minus 1.1. Now, with fractions, when we have fractions involved, you're actually breaking this down because the whole entire fraction is the radicand. What you're doing is you're finding this individually. You're actually finding the square root of 36 for the numerator, and then the square root of 169 for the denominator. So what is the square root of 36? 6, right? Because 6 times 6 is going to give us 36. And then what about the square root of 169? 13. Very good. 13. Okay, so we have 6 over 13. But again, because it doesn't state whether we want the positive or a negative, both would be suitable answers. So positive or negative 6 over 13. Now, square root of 30 happens to be an irrational number, but what we're going to do in this situation is we're going to estimate the value. And to estimate the value, we have to identify what perfect squares happen to be surrounding the square root of 30. So I'm going to write this down, that this is not a perfect square. And since it's not a perfect square, we're going to go ahead and estimate because we're not using calculators. So to estimate it, what you're going to do is you're going to find the two perfect squares that it falls between. So who can tell me what is a perfect square that is smaller than 30? Divya? Which is what? So 25. 25 happens to be a perfect square that is smaller than 30. Okay, so we have square root of 25. We have square root of 30. What is a perfect square that is larger than 30? Bridget? 36. Square root of 36 is the next perfect square above 30. Okay, there are several perfect squares above 30. There are several perfect squares below 30, but you want to do the ones that are directly in between. Okay, which ones are, you know, the end points of them. So here we have square root of 25 and square root of 36. Now, how far apart is 25 from 30? What kind of gap is that? 5, right? So I'm going to write that this is a gap of 5. What about from 30 to 36? What kind of gap is that? 6. Okay, so 25 is only 5 units away from 30. 36 is 6 units away from 30. So it's closer to 25. It's closer to the square root of 25. So we can estimate that it's about 5. That's our estimation. So square root of 30 is approximately a plus or minus 5. Okay, I want you guys to do number 6, 7, and 8 on your own. All right, let's go ahead and go over this. So problem number 6, we have the square root of 225 over 625. Who can tell me what they got as their simplified answer? Come on, Elijah, what did you get? Huh? What times itself can give you 225? You gotta try to think. I mean, what's 10 times 10? Huh? Okay, so we know it's got to be bigger than that. So pick another number. Pick a number bigger than 10. Okay, so what's 17 times 17? It's going to be bigger than 225. So go smaller. Go with a number that you do know. Do you know what 12 times 12 is? What is that? $144. Okay, so then go to the next. Do 13 times 13. It's 169. 14 times 14 is 196. 15 times 15 is 225. Okay, so you gotta try and think. Now, that's the list that I'm going to be giving you guys today. The list that you're going to have to memorize. Okay, it's going to be part of it. So guys, the square root of 225 is going to be 15. You want to break these down into individual parts. Anybody know what the square root of 625 is? Bridget? 25. So we get 15 over 25. However, this can be simplified. They both happen to be divisible by 5. Both of these values happen to be divisible by 5. So it's going to give us plus or minus 3/5. Always want to simplify your answers if you can. Okay, number 7, we have the negative square root of 400. The negative square root of 400 is going to be negative 20. Okay, because 20 times 20 will give you 400. So negative 20. And then number 8, square root of 54, that is not a perfect square, so we do need to identify the two values, or two perfect squares that happen to surround it. Who can raise their hand and tell me what perfect square is smaller than 54? Nicholas? 49. So we have the square root of 49. Then we've got square root of 50. And then what perfect square happens to be larger than 54? Trying? Huh? 64. Oh, sorry. Thank you. Thank you very much. All right, so now we have to find out what's the gap. So what's the gap between 49 and 54? 5. Gap between 54 and 64? 10. So it's closer to the 49. Okay, so it's going to be approximately the square root of 49, which is 7. So we have plus or minus 7, about. Okay? Any questions? Let's go on to the last page then. Cube roots. Cube roots are very similar to square roots, but instead of it being a number times itself, it's a number times itself again. So for example, the cubed root of 8 would be 2, because 2 times 2 times 2 will give you 8. So you're looking for a value that when you multiply it by itself 3 separate times, it'll come out to the radicand. Okay, so for here, with cubed roots, it's either going to be a positive or it's going to be a negative. It can't be both. Can't be positive and negative, okay? Because a positive times a positive times a positive is going to give you a positive answer. A negative times a negative times a negative will give you a negative answer. So here, when we're talking about the cubed root of 125, we're identifying what times itself again is going to equal 125. It's a pretty simple guess, because if it ends in a 5, what do you think it's going to have to also be? A 5. Okay, so it's going to have a 5 involved. It happens to be 5 times 5, which is 25, times another 5, which gives you 125. So this is going to be perfectly 5. Because, and I'll write the because here, 5 times 5 times 5 equals 125. Okay, so the answer in this case is going to be 5. For here, because we have a negative 64, we know that our answer is going to be a negative. So what do you think? Piece it together. We already know 2 times 2 times 2 is going to give us 8, so it can't be that. Let's go with a 3. What's 3 times 3? And what's 9 times 3? 27. Can't be that. Okay, let's go up to the next number. What's 4 times 4? 16 times 4? 64. So there's our response. Negative 4, because of the fact that it's a negative 64. And that again is because negative 4 times negative 4 times negative 4 is going to equal negative 64. Same idea or same concept involving the fractions. You find the cubed root of the numerator and then the cubed root of the denominator. So you can tell me, what is the cubed root of 216? What times itself again do you think is going to yield 216? Well, we already know that 5 times 5 times 5 is 125, so we're going to have to go up from there. What do you think, Divya? Not 7. 7 times 7 times 7 is going to actually give us 343. 6. Okay, think 6 times 6 is 36. 36 times 6 is going to give us 216. So this comes out to 6. The cubed root of 343 is going to come out to 7. So you get 6 over 7 as your answer. Okay. Again, you're going to be having a listing of perfect squares and perfect cubes that you'll have to memorize. These will become a lot easier for you. Now, when we're working it out in equation form, to solve equations that have exponents, all you're doing is just taking the root. Okay, you're just taking the radical. So to solve x squared equals 196, you're just going to take the inverse power, which is a root. So let me write that off to the side. The inverse of a power is a root. So if it's to the second power, then it's the square root. If it's raised to the third power, it's a cubed root. If you're raising it to the fourth power, you're going to take a fourth root. You're going to take the opposite root. Okay, so this happens to be x squared. So in order to be able to solve that, we're just going to take the square root of x squared, and that means you have to take the square root of 196. Square root of x squared just comes out to x, and then the square root of 196 is going to come out to 14. It could be a plus or a minus, we don't know. It just depends on what it asks for. Same thing for our cubed roots. You would just be taking the cubed root of x to the third power, which would give us x, and then you would have to take the cubed root of 8, which is going to come out to a positive 2. Now, one thing that I do want to make sure that you understand or make note of. Yep, she's on her way. Maya, make sure that you check online tonight for the notes and assignment. And here is the perfect squares and perfect cubes list that you're going to need to memorize, because for tomorrow's activity, we're going to be working with those. Okay? All right. So one thing that you want to make note, a negative square root of 16 is not the same thing as a square root of negative 16. If we take the negative square root of 16, that comes out to negative 4. But for square root of negative 16, this is going to provide an error. If you try to do this inside of a calculator, it's going to spit out a syntax error, because this is actually called an imaginary number. So just like we had the list of all real numbers, there are such things as imaginary numbers. And imaginary numbers have negatives inside of radicals. So if you want to get down to what this really is, this is considered 4i. And I'll even show you why. So our imaginary numbers, they actually repeat on a cycle of 4. There's a repetition of 4. So the value I, your very first imaginary number, is actually a square root of a negative 1. When you do I squared is just the value negative 1. So negative 1 is actually considered to be an imaginary number as well. If you have I to the third power, I cubed, that's the negative square root of negative 1. And then I to the fourth power is just a positive 1. And then the cycle repeats itself. I to the fifth power is square root of negative 1. So I to the fifth is the square root of negative 1. I to the sixth is negative 1. I to the seventh is the negative square root of negative 1. I to the eighth is a positive 1. And it just keeps repeating over and over and over again. So these are how we identify imaginary numbers. Values that have negatives inside of the radicand, that's not allowed in real number form. So then we go to our imaginary set. You don't need to know this. This is just something, an interesting little tidbit, but you will be working through these when you get into high school. Michael's like, oh dear God. It's actually not that hard. I think imaginary numbers are very, very simple. Okay, what you're going to be doing now is I'm going to be giving you guys a set of perfect squares and perfect cubes. You're going to be filling it out, and yes, you're filling it out without a calculator, but it's easy. If you know that 1 squared is equal to 1, then the square root of 1 is equal to 1. 2 squared is equal to 4, so square root of 4 is equal to 2. 3 squared is equal to 9. 9 squared is, or the square root of 9 is equal to 3. It's just side by side, so it correlates to each other. So if you go all the way down here to the very bottom, if you are like, I have no idea what the square root of 576 is without a calculator, yes you do, it's right next to it. 24 to the second power is 576, so square root of 576 is 24. You only have to worry about the positive parts, okay? You will be taking a quiz tomorrow without this. And I'm going to be picking probably like 4 or 5 perfect cubes and about 15 perfect squares randomly. Don't know which ones I'm going to be picking yet. So you need to make sure you have the whole thing memorized and it is timed. Okay? Any questions? All right.